Hey y'all, today we're going to be talking about the topic of functions of several variables. It turns out in the real world, not all things depend on just a single input. Therefore, we need to expand our language as far as functions go to include that which has multiple inputs. From there, we'll start discovering calculus on functions of several variables. Without further ado, let's dive in. Let's first off talk about functions of two variables. Now, function f of two independent variables, let's call them x and y, is just a rule involving those x's and y's that produces an output, let's call it z. That is, f of x comma y equals z. Now, in the example below, let's go ahead and consider f of x comma y equals a square root of 64 minus x squared minus y squared. If we want to talk about evaluating a point, let's say 3, 0, all you would have to do is respectively plug in 3 and 0 for x and y. So therefore, f of 3, 0 would just be 64 minus 3 squared minus 0 squared. This is just the square root of 64 minus 9, or the square root of 55. So the z value assigned to the pair 3, 0 would be the square root of 65. We could also play this game for maybe a point -1, 2, in which when we go ahead and plug them in, -1 for x, 64 minus -1 squared minus 2 squared would give us a z value, upon evaluating, of 64 minus 1 minus 4, so 64 minus 5, or just the square root of 59. That's how we're going to go ahead and find the z values given x and y pair. Now, it is important to note that these functions of two variables, f of x comma y, are actually going to have a very unique difference compared to functions of just one variable. That is, we must draw a third z-axis in order to actually map them. These functions look 3D upon mapping. How we're going to map them is by, for every single x and y pair, which you'll find down here, you'll put on its z-axis the z value that the function shoots out. So for instance, if I were to figure out f of 0, 8, I would get the answer, the z value 0. Which indicates that the point 0, 8, 0, where we have x, y, z, that point is on my graph. Over here, if I were to throw that on there, on my x-axis, I would be 0, so I'm right here. My y-axis, I march all the way out to 8. 1, 2, 3, 4, 5, 6, 7, 8. And then on my z-axis, I'm 0. So this thing is really flat right there on that line. F of 0, 0 equals 64 in this case. Therefore, the point 0, 0, it's not 64, it equals 8. The point 0, 0, 8 is on my graph as well. I go 0 on the x-axis, so I'm stuck at the origin. I go 0 on the y-axis, so I'm stuck right here on this line. And then I go up 8. 1, 2, 3, 4, 5, 6, 7, 8. That point is also on. Now it turns out if we were to fill in every single point, what we would end up getting is a circle down here, kind of on the plane. And then looks a little bit like a dome. And all these points will just kind of fill in the outer shell of the dome. These functions really do map into 3D space. It takes a little bit to get used to, but think of your x, y, and z as almost standing in the corner of a room. If you're standing in the corner, and I give you an x, y, z coordinate, think about walking so many steps this way or this way as your x, so many steps this way or this way as your y, and then ultimately your height in the room as your z-coordinate. To solidify our understanding of evaluating these functions at given points, let's consider the following. Evaluate the following given that f of x comma y is equal to x squared plus x times y. First and foremost, let's see what happens at 0 comma 0. To evaluate this, just plug in 0 for x and 0 for y. Gives us a point 0. Therefore, the point 0 comma 0 comma 0, where we have x, y, and z respectively, is a point on our map. F of 2 comma negative 1 is given by, well, plug in 2 for x, 2 squared, plus 2, and then plug in negative 1 for y. So what do we get? We get 4 minus 2. This guy gives me 2. So therefore the point 2 comma negative 1 comma 2 is a point on our map. Last but not least, let's consider the point negative 1 comma 5. Plug in negative 1 for x, so negative 1 squared plus negative 1, and then plug in 5 for y. Well, negative 1 squared is a positive 1, minus 5 gives me a negative 4. So ultimately, the point negative 1 comma 5 comma negative 4 is a point on our function. This is exactly how we're going to evaluate these functions. Not too bad, just plug them in. And then note that our output will be a point in three-dimensional space. An important question then pops up. Why would we just stop at 2? Well, it turns out we don't have to. You can have as many independent variables as you like. Now, the only thing to note, and by the way, our evaluation would be treated the same, just plug in respectively for what value is corresponding to what point, what coordinate. The only thing to note then would be if you have n independent variables, the graph of the function will be n plus 1 dimensional. So, for example, in our previous one, we had 2 independent variables, x and y, and our graph appeared 3-dimensional. If we had 4 independent variables, we would appear 5-dimensional. So this stuff starts to get quite out of hand pretty quick as far as actually graphing these things goes. So what we'll mostly be concerned with is functions of 2 independent variables. Now, since we're in calculus class, I do have to ask the following question. How the heck do I define a rate of change on a function that maps in the 3D surface? It doesn't necessarily seem apparent right away. Now, looking at the following, what we could say is, well, shoot, if we just had this part of it right here and it was just kind of smushed flat, then we'd be able to do that. And in a sense, that's actually exactly what we're going to be doing. To further demonstrate this, let's go ahead and view this picture, followed by the commentary on the next slide.
So to imagine how we're going to take derivatives and measure rates of change with functions of 2 variables, what I first want you to visualize is being this poor guy stuck right by a wave. As he's standing there, and let's say he froze time perfectly so this photo actually makes sense, he wouldn't really be able to tell you if you asked him, hey, at what rate of change is the water? He wouldn't be able to tell you that unless you gave him a direction. So, for instance, if he were to look left and right, the water level would appear perfectly level. He would say that the rate of change of the water is absolutely 0. However, if you look forward and backwards, he would be able to say, wow, the rate of change, the water behind him is at least 5 feet taller than him. So he would say the rate of change is pretty large. So therefore, when we're in these 3D surfaces, we really have to indicate a direction that we're talking about a derivative. So let's go ahead and let's go ahead and picture this new function right here. It looks like a perfect little horse saddle, and we got this red point in the middle. And let's say that the x-axis is going from your upper right to your bottom left, while the y-axis is going from your upper left to your bottom right. If we were wanting to take the derivative of this, you could picture yourself standing right where that red dot is. Now imagine a plane slicing right through you, right through the axis, and which you're wanting to measure, either left to right or forward and backwards, along the x direction or along the y direction. Now let's focus on the x direction. In green, you can see a plane cutting through. Notice what's in the intersection of the green plane and our function. It turns out, as you can see in kind of a solid red line, that we're left with a function of a single variable. And guess what we know how to derive? A single variable. Now the act of putting a plane in and slicing it through our function is actually the act of holding, in this case, y constant. So in order to take a derivative, what we're going to have to do is hold one variable constant while letting the other one change. If we're holding y constant, we get this green picture. If we're holding x constant, we would get a plane slicing through in a perpendicular direction to the one that we have shown right now.
Now, as you've seen on the previous slide, in order to talk about a rate of change of a function of two variables, we need to hold one of the variables constant. That means we only need to look at the rate of change of one variable. That's the only real way we can handle it as of right now. So, just like we developed the derivative for functions of one variable through a difference quotient, it turns out that exact same derivative that I just described can be derived from a difference quotient with a function of two variables. Now here's our difference quotient for a function of two variables. F of x plus h comma y minus f of x comma y divided by h. This difference quotient is measuring the rate of change in the x direction, in the x variable. And we actually have an analogous version for the rate of change in the y direction, given by the limit as h approaches 0 of f of x comma y plus h minus f of x comma y divided by h. The difference is where the plus h is. X over here, y over here. This measures the rate of change in the x direction, and this measures the rate of change in the y direction. That's how we're going to start to define a derivative in two-dimensional space. So let's consider an example. Given f of x comma y equals x squared minus 2y, find the limit as h goes to 0 of f of x plus h comma y minus f of x comma y divided by h. Well, just like before, we're actually just going to plug in x plus h wherever you see an x. Over here, we would have plugged in y plus h wherever we saw a y. Up to then, it's just going to be some algebra beyond that. So, f of x plus h. Plug in x plus h wherever you see an x, and plug in y wherever you see a y, i.e. don't change y. That will just be x plus h squared minus 2y minus the original function, x squared minus 2y, divided by h. From here, start doing some algebra. We can go ahead and square out x plus h squared, giving me the limit as h goes to 0 of x squared plus 2xh plus h squared minus 2y. Distribute in the negative over here, minus x squared plus 2y. And don't forget we're dividing by h. From here, notice that our two y's cancel, as well as our x squareds. This just leaves me with the limit as h goes to 0 of 2xh plus h squared on top, all divided by h. From here, notice that we can factor out an h on top, giving me 2x plus h, and then ultimately we can cancel an h. This leaves me with the limit as h goes to 0 of 2x plus h, which upon plugging in 0 for h, gives me an answer of 2x. Now this process is entirely similar for finding the rate of change with respect to y, so f of x comma y plus h, but the answers will give you two entirely different things. This answer tells me the rate of change in terms of the x direction, while the other would tell me the rate of change in terms of the y direction. To find the rate of change in the y direction, we're going to use the difference quotient, the limit, as h goes to 0, of f of x comma y plus h minus f of x comma y divided by h. As we have the plus h attached to the y, this will measure the rate of change in the y direction while keeping x constant. So therefore, let's go ahead and find this for the function f of x comma y is equal to x squared minus 2y. As normal, go ahead and plug in y plus h wherever you see a y while keeping x the same. So f of x comma y plus h is the function x squared minus 2 times y plus h. Now subtract off the entire function, original x squared minus 2y, and then remember we're still dividing by h. From here, go ahead and simplify as normal. This guy we can distribute in the negative 2, giving me x squared minus 2y minus 2h. And then over here we can distribute in the negative. Minus x squared plus 2y. All divided by h. Now notice the magic happened. Just like the regular difference quotient from functions of one variable, a lot of cancellation should happen. The minus 2y cancels out with the plus 2y, and the minus x squared cancels out with the plus x squared, leaving me with just the limit as h goes to 0 of negative 2h divided by h. Before taking the limit, we notice that the h's cancel, leaving me with the limit as h approaches 0 of just the constant negative 2, which as typical equals negative 2. This is how we're going to go ahead and handle the difference quotient with respect to y changing. Hey y'all, thanks for tuning in today as we discuss functions of several variables. Now these functions of several variables were handy when we have scenarios that depend on more than one input. Happens all the time. Now, since these functions map, if we have a function of two independent variables, it maps to a 3D space. All of a sudden, discussing the rate of change tends to be hard. Imagine being in a swimming pool again. So what we have to do is freeze time and look at the rate of change in either the x direction or the y direction. We can only do that good right now where we limit ourselves to measuring the rate of change one way, which in effect is measuring the rate of change of a function of just one variable. Now we can only do that through the difference quotient right now, but next time we'll get shortcuts for how to do that. So, without further ado, go ahead and attempt your homework. Email me if you have any questions, and as always, thanks for watching.